In this module, module 4.3, we're going to explore some properties of normal distribution. Specifically, we're going to look at what happens when you evaluate variance of higher order powers of x. And we're going to see that it quickly gets complicated when you have x raised to a higher power. We'll start with x squared, and we'll see that x squared in turn depends on expected value of x to a higher power, x to the power 4, it turns out. And therefore, quickly variance calculation becomes more and more complicated. But before we go there, I want to review something that we've discussed in the past, and that is the measures of central tendency. We talked about how mode, median, and mean are measures of central tendency. So the definitions of mean, median, and mode are: mean is the expected value of x. Expected value of any quantity is that quantity times the PDF integrated between the limits of minus infinity to plus infinity. And median is the value at which the probability turns out to be 0.5. So it's minus infinity to some value at which the probability, the CDF, turns out to be 0.5. That's the definition of median. And mode is the value at which the slope is 0, or the function has a peak. So that's the definition of mode. So now I'm going to show you the formula for the variance of x squared and illustrate some basic issue governing variance of any quantity. So we see that variance of x squared depends on expected value of x to the power 4. And the expected value of x cubed is given here. Expected value of x to the power 4 is given here. All of these formulae are only valid for normally distributed random variables because they use the symmetry of the normal distribution. Normal distribution is convenient because of its symmetry. The other distributions we will study in this class, none of them are symmetric. So this formula is convenient for normal distribution. I'll briefly explain how this formula comes about, and I will give you a handout that shows the derivation in greater detail. So I'll briefly motivate this formula and illustrate the challenge of calculating variance of higher powers. So if I take variance v of x, by definition, variance of v of x is integral going from minus infinity to plus infinity, x minus x bar squared f of x dx. And if I go to which we know is expected value of x minus x bar squared. Now, if I take the variance of x squared, the variance of x squared is expected value of x squared minus expected value of x squared, this whole thing squared. And this I can write as expected value of x to the power 4 minus 2 times x squared times expected value of x squared plus expected value of x squared, this whole squared. So as you can see, expected value of the variance of x squared is going to be expected value of x to the power 4 minus 2 times expected value of x squared times expected value of x squared, and plus expected value of x squared whole squared. So this again is expected value of x to the power 4 minus expected value of x squared, the whole squared. So the key point here is that variance of x squared depends on expected value of x to the power 4. Things quickly get more and more complicated as you go to higher and higher powers of x. So if you want variance of x cubed, it's going to be dependent on x to the power 6 and so on. So this is a challenge of calculating variance of complex nonlinear functions that we will address later in the semester using what's called the first order approximation, first order reliability approximation. Let's go back. There is a general derivation, and this is intended as a handout. This is not something I'll go through in great deal of depth, but what it gives you is a derivation for variance of x squared in detail for normal distribution. So you can go through and calculate expected value of x cubed, and in calculating expected value of x cubed, you will make the assumption that expected value, this is a normal distribution due to symmetry about the mean. There is no skewness. What is skewness? Skewness is expected value of x minus x cubed is defined as skewness. And I'm similarly, so this allows us to write expected value of x cubed. Expected value of x minus x cubed is a skewness. And similarly, now we can go through and calculate expected value of x to the power 4, x minus x to the x bar to the power 4, and from which we can evaluate expected value of x minus x bar to the power 4. This is quite involved. I'll give this as a handout. And when you integrate, finally, you can derive the expected value of x to the power 4. And from once you know expected value of x to the power 4, you can estimate the variance of x squared. And those are the formulae that are given in the slide here. Now, before I leave this module, I just want to leave with two definitions. So we know that variance is defined. We've already defined variance here. So now I'm going to define skewness. These are not concepts that we will use. Skewness by definition is expected value of x minus x bar cubed, and that is integral going from minus infinity to plus infinity x minus x bar cubed f of x dx, and kurtosis is defined as expected value of x minus x bar to the power 4. It's integral going from minus infinity to plus infinity x minus x bar to the power 4 f of x dx. These are concepts, these are statistical concepts, but in engineering practice, it's, we won't use these simply because these are very hard to estimate. So if you think of the mean value, so the variance represents the second moment about mean, and the skewness represents third moment about mean, and this is the fourth moment about mean. So variance itself, as I described, is very challenging to estimate. Skewness and kurtosis are even more challenging to estimate, and that's the reason why they're usually not used in engineering practice. For every variable, it's very hard. If you have a random variable, a design parameter that's random, to estimate skewness is very hard for that parameter, and even variances get complicated. So for that reason, we rarely use skewness and kurtosis. So with that, I'm going to stop this module.